Hello everyone, welcome back to another lesson with me, Mr. Wong. Today we're going to be looking at Module 7 in Physics, the nature of light. Inquiry question 1, electromagnetism. Before we begin, let's have a look at some questions about electromagnetic waves and break them down as a starting point for this lesson. So question 1 says, identify the different types of electromagnetic waves. If we can just use three simple examples, we have microwaves, we have radio waves, and we also have X-rays. Now, in question 2, identify the applications of the electromagnetic waves listed. So, with microwaves, we can use that for cooking, to reheat food, or to cook food. Radio waves, we can use that for communication technology, so radio sound signals and all that. And then we can also use X-rays for medical imaging for things like bone structure and all that. Number 3, does an electromagnetic wave require a medium to propagate? In another case, does it need a medium to move? Now, an electromagnetic wave only depends on the propagation of electric and magnetic fields, and so no, it is self-propagating. It does not require a medium to move. In today's lesson, we're going to explore the early theories of electromagnetism. We're going to look at how Maxwell unified the theory of electricity and magnetism, and hopefully by the end of this lesson, you should be able to make some connections between the production of electromagnetic waves and the predictions that Maxwell made for them. These are the textbook reference pages, so please have a read there as well. So the topic we're looking at firstly is Maxwell's contribution to unification of electricity and magnetism. We will look into how he predicted the velocity of electromagnetic waves, and we'll also briefly talk about how electromagnetic waves are produced based on these little predictions that Maxwell created. We talked about mechanical waves, we talked about electromagnetic waves. Mechanical waves are just waves that require a medium to propagate, so need some kind of particles in some space to make it propagate. That's like sound waves, that's water waves, things like that. Electromagnetic waves are slightly different. These are dictated or propagate because of electric and magnetic fields oscillating and changing. So we have mechanical wave examples, water ripples, and sound. We also have electromagnetic waves, so we have microwaves, we have ultraviolet light. These are two examples of electromagnetic waves. A little interesting fact about electromagnetic waves is the fact that they are continuous. So because they don't require a medium to propagate, they only require changing electric and magnetic field. Once an electromagnetic wave has been generated, they are continuously moving throughout the entire universe. So let's say with the example of light, which is a type of electromagnetic wave, when a star dies, it will emit a big bright light and it travels throughout the universe. Now, back in 1054 AD, the Chinese actually saw a supernova, and supposedly, according to that record, they saw a really bright light for 20 days straight, and it was just in their observations there. So that was one of the early observations of the supernova, and this is what the supernova they believe that the Chinese saw way back. So obviously, we're not in 1054 AD, but as I said, the images of electromagnetic waves are ever continuously moving around the universe. If we happen to come across it in our capture, we will be able to see it as well. So an electromagnetic wave, I've already talked about it. It's just an oscillation of magnetic and electric fields acting perpendicular to each other. There is no physical vibrations in an electromagnetic wave. There is no physical vibrations in an electromagnetic wave. It's just purely oscillations of electric and magnetic fields. When we have a current carrying charge, okay, this man here came up with the idea that a current carrying charge will produce a magnetic field. So current going up, and then you see the magnetic field being generated around the conductor. What we also see is from Michael Faraday, the induction law. So we said that if there is a changing magnetic field or magnetic flux, we will generate what we would call electric fields. We would generate EMF. So along came a guy called James Maxwell from Scotland back in 1830 or so, and he started looking into these properties of electricity and magnetism. So his final conclusion was that when an oscillating charge has a changing electric field, it will also induce a magnetic field as well. Let's have a look at how he came to that conclusion. So the conclusion he came up with was actually through these 4 basic equations that he derived for himself. And let's just make this very clear. This theory of electromagnetism, or the theory of, let's just make this clear, the theory of electromagnetic waves, a scientific theory, is something that has been tested and has considerable explanatory capabilities. So what do we mean by that? We mean that it can be proven with some kind of mathematical equation, and later on it can be tested. Now, not all scientific theories, when they first come out, have been tested straight away, but for it to be a solid scientific theory, it has to have credible mathematics behind it, and also you can produce experiments that can match up to this initial hypothesis. Well, we do talk about scientific theory in general public. So when we say theory in general public, that's where the misconception is. A theory has been based off some facts that we already know. Okay, it's not an assumption. The significance of Maxwell's theory, he combined unrelated observations and experiments and equations about electricity, magnetism, and optics into one consistent theory. Today we're just going to focus mostly on the electricity and magnetism section, but we will briefly talk about the optics as well. So these are the 4 equations that Maxwell derived. He has Gauss' law, he has Gauss' law for magnetism, he has Faraday's law, and he has the Ampere-Maxwell law. We're going to look and break down each of these, what they mean, and what significance do they have to the overall narrative of electricity and magnetism. Before we go to that, you'll see in some of these formulas, you have mu naught and epsilon naught. Okay, so mu naught is the permeability of free space. This is what we call the magnetic constant. And essentially, a simple definition is the proportionality of how strong the magnetic field strength would be in a vacuum. Okay, so it's the resistivity that a magnetic field would have inside a vacuum of space. It's a measured value, so it's measured to be 4 pi times 10 to the power 7 meters kilograms per coulomb squared. The electric constant, the permittivity of free space, that's essentially saying how strong can an electric field be in the resistance of vacuum. Okay, and so that's what we have here. Just to give you a better understanding of the permeability of free space, here's just a diagram I took off one of the videos. So an electric field is going to go from the positive plate to the negative plate. Now, under normal conditions, like let's say lab conditions, there will be air resisting the electric fields passing through. Okay, we have matter passing through. Okay, so there's resistance. So permittivity is just talking about the resistance. When we talk about permittivity of free space, we're talking about the resistance in a vacuum. And so that can be measured as a constant. In Maxwell's very first equation, we have Gauss's law. And Gauss's law states that a net charge inside an enclosed surface, so a Gaussian surface, so any charge that's locked inside any surface, will always experience some amount of electric flux. So to put that simply, an electric charge will always exert an electric field. Okay? And so if we have a look and break down this equation, capital E represents the electric field. Delta A encapsulates the area surface that the electric fields are coming from. So these factors, the electric field is dictated by the magnitude of the charged particle. So if we look at, let's say, a proton or an electron, and then it's also dictated by the permittivity of free space, so the resistance that the electric field experiences in a vacuum. The next one we have is Maxwell's second law, or Maxwell's second equation, which is Gauss's law for magnetism. So his idea is very simple. The idea is that magnetic flux through any enclosed surface is equal to 0. So a magnet will always, if I just draw that out, so if we have a magnet, let's say one side is north, one side is south, you'll have magnetic fields coming out of the north pole, and then you'll have it looping back into the south pole here, okay? So the second equation essentially states that anything inside this magnet here, there is no net magnetic flux going away from the magnet, nor is there any net flux going into the magnet. They essentially cancel each other out. So there is no independent north pole or independent south pole in any magnet. Okay? This means any magnetic fields that end up leaving our magnet will come back to it at the end. So they eventually reconnect with each other. And so that's why inside that surface, the net magnetic flux is equal to 0. We know that B represents the magnetic field. We know that delta A represents the area. And so if we look at this diagram here, the same idea holds true. If you have a magnet, it's going to produce magnetic fields that go out, but then they will eventually come back in. So that's why the net the net magnetic flux inside is equal to 0, because you have equal amounts going outside the magnet and equal amounts going back into the magnet. The next we have is, what if you try to cut a magnet into half? What would happen there? Well, I can cut the magnet into a half, and this bit we have here, this section we have here, that's not going to become south, that's not going to become a monopole, but if you keep cutting a magnet in half, that area where you cut becomes the opposite polarity end. Okay, so this one becomes north, and this one becomes south. You can keep cutting it, and if I keep cutting it this way, this becomes south, this becomes the north pole of the magnet. The third equation we all know from module 6 is Faraday's law, and that's just to say if we have a changing magnetic flux, so a changing magnetic flux will produce an electric field or produce EMF as well. And we know that from the equation, E is just the magnetic field. We said that magnetic flux is from the change over time and inside a closed loop, and so change in magnetic flux as well. So we're saying when we have a change in magnetic flux over time inside a loop surface, so let's say a circuit wire, an electric field will be induced. Let's just quickly revise back on Faraday's law. We know that Faraday's law states if we have a changing magnetic flux in a conductor, we can induce an electric field, we can induce EMF. So if I have a look here, you can see that the voltmeter is changing even though my magnet is not quite near the conductor. If we put it in, we can see there is light being produced because of the electrical energy being converted into light. So what we can deem here is, from Faraday's law, a changing magnetic flux through a coil, a conductor coil, will induce an EMF. That EMF will induce a current, and that current obviously will create an electric field because of it. Maxwell's fourth equation is Ampere's law. So he essentially says when a current moving charge in some kind of conductor is holding current, a magnetic field will be created. He also showed that when you have two wires of current carrying charge, the wires can experience a force of attraction or a force of repulsion. And to break this down, he looked at the magnetic fields. He also looked at the fact of permeability of free space. So he's saying a magnetic field being induced is dictated by the current and also the permeability of free space or magnetic fields. And we all know the concept of Faraday's law, and so the idea is, can the reverse of Faraday's law be true? So if I have, instead of a changing magnetic field, I have a changing electric field, will I induce a magnetic field back? And that's essentially what he came up with as the second equation here. This equation here is known as the displacement current, and it's the idea that Maxwell came up with to symbolize how changing electric fields can also induce a magnetic field as well. So we have two bits. The first bit is this bit here. We're saying this bit, a moving charge will induce a magnetic field. We're also saying a moving electric field will also produce a magnetic field. So we have just moving charges, and then from the charges there is electric field, and when that electric field is moving because of these charges, we also induce a magnetic field. So magnetic field there. And as you can see, there are two factors that influence the displacement current. The two constants, the magnetic constant and the electric constant. And so this is actually very important because these are the two constants that Maxwell will later on use to work out the speed of electromagnetic waves. So there you have it. This is just going back to the four equations he looked at. So Gauss's law for electric flux, Gauss's law for magnetic flux. You can see that if electric fields or electric charges create magnetic flux, so here are the four equations again. So Gauss's law for electricity states that an electric charge will induce an electric flux. Gauss's law for magnetic fields says that magnetic objects will create magnetic flux. However, the overall flux inside the object is net zero. So an electric charge can create fields. Magnets can create fields as well. He showed that Faraday's law, if you have a changing magnetic flux, you'll produce an electric field. And he showed if you have a changing electric field. And he also showed a changing electric field would induce a magnetic field as well. So he's showing that instead of saying these two are separate concepts, instead of saying these two are separate to each other like 1 and 2, we're saying in fact that's not true. These both interfere with each other. These both interact with our relationship of the world. He's trying to show that changing electric fields will induce magnetic fields and vice versa. So they actually influence each other. They are variables that would affect each other. And that's a very groundbreaking discovery. Here's another summary of the different ways you can write Maxwell's equations, so I'll leave that there for now. Okay, let's have a look at the thought experiment that James Maxwell came up with. So he was thinking, if I have an electric charge attached to some kind of pole, and then I allow the charge to move up and down, so allow it to oscillate in both directions. He predicted that the electric charge, if it's moving up and down, will obviously produce a changing electric field. And so based on what he knew from the Ampere-Maxwell law, if you have a changing electric field, you induce a changing magnetic field. So let's play that through. And so you can see the magnetic field and the electric field are perpendicular to each other. So that's how he came up with the idea that electromagnetic waves are self-propagating. So this charged particle that's oscillating will induce an electromagnetic wave that has a self-propagating electric field and a self-propagating magnetic field. And this is the power of the thought experiment he came up with. Maxwell has essentially shown if you have a charged particle and you make it move up and down, you will change the direction of its electric field. So if we have a changing electric field, it's going to induce a magnetic field that's acting perpendicular to that electric field. So this is showing how he's combining Faraday's law and Ampere-Maxwell's law equations together to come up with the idea that if you move and oscillate an electric charge, that charge will create an electric field. The electric field will create a magnetic field and vice versa back because of these changes. And because of these changes, you'll get an electromagnetic wave being produced because it's going to be self-propagating. Okay? The electric field's going to keep moving and the magnetic field's going to keep changing with it. They're going to keep self-inducing each other, and that's why we're saying that. And that's why we're saying that an electromagnetic wave is self-propagating because the two factors that work with the production of the electromagnetic wave is already there. That's why it doesn't need a medium to move. And so what did Maxwell have to say overall? He basically said that an electromagnetic wave is self-propagating. A changing electric field will induce a changing magnetic field and vice versa. And that's how he came up with the unification of electricity and magnetism, and this is how he also came up with the proposal of the electromagnetic wave. And so the next part we have is how did he come up with the speed of the electromagnetic wave? Now, back in 1856, a guy called Wilhelm and Rudolf were using discharge Leyden jars to work out the ratio between the magnetic constant and the electric constant. What they found was a simple relationship shown here. So they found the ratio between the two constants was given by this mathematical equation. And what Maxwell managed to do, he made the wave equation and he found that the wave equation to find the speed of electromagnetic waves was given as 1 over v squared equals to epsilon naught and mu naught. If you flip this over, he found in order to find the electromagnetic wave speed, it just depended on the two constants. So if we look at that number, we already know what epsilon naught is and what mu naught is. So mu naught is here, epsilon naught is here. So if we put the numbers in, we'll find that substitute the numbers in, we'll find that the velocity of the electromagnetic waves is equal to 2.998 times 10 to the power of 8 meters per second. Now our current knowledge of the speed of light is very similar to this number, but we'll also do some comparisons of the numbers of the speed of light back then during Maxwell's time and how that actually showed that light could just be part of the electromagnetic spectrum. But before we go on, let's just quickly summarize his contributions so far. Essentially, he aligned the different observations and experiments to show that electricity, magnetism, and then later on light being under the same theory for physics. He showed that because light and electromagnetic waves have the same speed, then light was also propagation of electric and magnetic fields. and these fields would just essentially vibrate perpendicular to each other. And so here we are in our lesson summary. We've covered quite a few points today. We looked at the magnetic constant, we've looked at the electric constant. We've also looked at Maxwell's 4 equations that he derived and how these 4 equations come together to make our understanding of electricity and magnetism into the universal theory of electromagnetism. We've also looked at how the speed of electromagnetic waves is only dictated by the magnetic constant and the electric constant, so we can measure it in a lab. So we've come across the speed of electromagnetic waves. In next lesson, we'll try and finish off the prediction of the speed of the wave with the speed of light, with some more history on how the speed of light was measured. And then we'll also look at the prediction that Maxwell created in the fact that electromagnetic waves aren't just one type, they actually come in many different types, which is known as the electromagnetic spectrum. But until then, here's some other videos to link to and future videos as well. And here's a link to future videos and the playlist for this module. I'm Mr. Wong. Thank you for joining, and I'll see you next time.